One of the most important solvents that we need to be familiar with is water. Water is the most common solvent found in nature. In a previous chapter, we saw how water molecules are polar molecules because when we look at the structure of water is a tetrahedral molecule that has polar bonds. And because this polarity is not symmetrical, water is a polar molecule. Due to the polarity of molecules, it's important that we know how to understand the behavior of substances when they encounter water. Water molecules to each other are going to be interacting via hydrogen bonding events. And we're going to see in this chapter and later in the semester how many biological compounds will be interacting with water via hydrogen bonds. Water is so important that the human body is actually mostly water. As we can see in the illustration on the right side of the slide, we can observe that the human body on average is 72% water. We observed before that in order to form a solution in water, since water is a polar molecule, specifically ionic solids need to interact with water via an ion dipole interaction in order to make a solution. The polar water molecules will become oriented. So the partial negative charge in the oxygen atoms will be interacting specifically with the cation in an ionic compound, while the partial positive charges in the hydrogens in the water will be pointing towards the anions in an ionic compound. Interestingly enough, not all ionic compounds are going to be soluble in water. When you have in a chemical formula a cation from group 1A, including sodium, lithium, potassium, rubidium, or you have ammonium, those compounds are always soluble without exception. So that means that any compounds that start with those elements will always be soluble. Additionally, there are two anions that are going to be always soluble in water, and those are nitrates and acetates. We can see that any chemical formula that has those anions, they don't have any exceptions. Next, we have the chlorides. Chlorides will also be soluble in water, but when we have chlorides paired with the cations silver, lead 2, mercury 2, or mercury 1, then the chlorides become insoluble. So the pairing of any chlorides with these will make them insoluble. Next, we have the sulfates. When it comes to sulfates, sulfates are soluble in water, except if they're paired with barium, strontium, lead 2, mercury 2, or mercury 1. Next, we have the carbonates. Carbonates tend to be insoluble in water, but there is a way to make carbonates soluble in water. That means if you have carbonates paired with anybody from 1A or ammonium, they become soluble. Lastly, we have phosphates. And phosphates tend to be insoluble in water. The only time that we can make phosphates be soluble is if they're paired with 1A elements or if they're paired with ammonium. Many hydrogen carbonates and phosphates tend to be soluble, as you can see down here. But overall, these are the solubility rules that you need to be familiar with. Let's actually do an application of how do we use these rules in reactions. One of the main applications when it comes to solubility rules is in the product prediction for double replacement reactions. In double replacement reactions, what we have overall, just to remind you, is that we're going to have two aqueous ionic compounds that are going to exchange ions. In order to represent this and use the solubility rules, I'm going to do examples A and B in the slide. In double replacement reactions, we may or may not have a precipitate form. A precipitate is going to be a solid form of an ionic compound, and this precipitate will form as long as that ionic compound is not soluble in water. So let's look at the first example. Sodium nitrate combines with lithium sulfate. When this happens, in order for us to predict the products, let's remind ourselves that in a double replacement reaction, we have an ionic compound that can be represented by letters A and B, combined with an ionic compound that can be represented by letters C and D. Next, we are going to assume that letter A represents a cation, letter B represents an anion, and similarly, C is an cation and D is an anion. Overall, in a double replacement reaction, these two ionic compounds are going to exchange partners. So we are going to have a new ionic compound represented by the letters A and D, and a new ionic compound represented by the letters C and B. Remember that the chemical formulas for ionic compounds is always cation followed by anion. So when we look at letter A, the ions for each of those two aqueous ionic compounds is going to be Na plus 1, NO3 minus 1. In the next compound, lithium plus 1, and then we have sulfate 2 negative. In order to predict the products, remember that there's going to be an exchange of ions, meaning that they're going to switch partners. So one of the compounds that we are going to be generating in this reaction is now when lithium combines with NO3. So if lithium combines with NO3, that makes the chemical formula LiNO3. The other compound that forms is going to be the one that comes from sodium and sulfate, Na plus 1, SO4 minus 2. So the chemical formula is Na2SO4. So when it comes to solubility rules, if something is soluble, we label it as aqueous because it can make a solution with water. But if something is insoluble, we're going to label it as solid because it's not going to be soluble in water. So when we look at all of these chemical formulas, sodium nitrate is soluble in water because it has an element from group 1A and it has a nitrate. And we can see that there's no exceptions for them and things are always soluble. So this is an aqueous compound or aqueous solution, I should say. Then we have lithium sulfates. Sulfates are soluble unless they're paired with this, but since lithium is not barium, strontium, lead-2, mercury 1, or mercury 2, then we know that lithium sulfate is also an aqueous solution. When we look at the product of this reaction, we have lithium nitrate as the first product. Lithium nitrate is going to be soluble in water, so we're going to label it as AQ because we have an element from 1A and we have NO3. Next, sodium sulfate, since sulfates are soluble and additionally that chemical formula has a cation from 1A, then that means that sodium sulfate is also aqueous. So the example for letter A is technically, in essence, going to be no reaction. And if you actually do it in the laboratory, since sodium nitrate and lithium sulfate are going to be clear, colorless liquids, we're not going to observe any changes. So as long as you have a double replacement reaction that results in the formation of two aqueous solutions, then we're going to see that no reaction is happening. Let's actually look at specifically letter B. In letter B, we have lead-2 nitrate combining with potassium phosphate. Lead-2 nitrate is going to be aqueous because nitrates don't have an exception. They're always soluble. Next, potassium phosphate, even though they're mostly insoluble because the phosphate is actually paired with somebody from 1A, that makes the phosphate soluble. So potassium phosphate is also an aqueous solution. The ions that make those two compounds are the following. For the first one is lead-2 and NO3 minus 1. For the next one is K1, so potassium plus 1, and then phosphate is minus 3. So the products of the reaction are going to be as follows. The first compound is going to be K plus 1, NO3 minus 1. So that chemical formula is KNO3. And the next product of the reaction is going to be Pb plus 2 combining with PO4 minus 3. So the chemical formula is Pb3, PO4, 2. Let's now determine if indeed we have formed a precipitate, meaning that we made an ionic compound that is not soluble in water. So when we look at KNO3, since KNO3 has nitrate in the chemical formula, and additionally, we have potassium, any of those two ions make a compound be soluble in water, so KNO3 is actually aqueous. When we have lead-2 phosphate, as we can observe, phosphates tend to be insoluble. And since in this chemical formula, we don't have a phosphate actually paired with anybody from 1A or ammonium, in this reaction, we actually have the formation of a precipitate. So since lead-2 phosphate is insoluble, we're going to put an S for solid in this reaction. So the reaction in B, one of the products will form a precipitate So that means that this is a double replacement. This is my shorthand for double replacement reaction. Before I move on, it is important that every time we have a double replacement reaction, we actually balance it. So when it comes to this, to balance the first reaction, I'm going to place a 2 before sodium nitrate, and I'm going to place a 2 before lithium nitrate. And now on both sides, I have 2 sodiums, 2 nitrates, 2 lithiums, and 1 sulfate. To balance letter B, I need a 3 before lead 2 nitrate, a 2 before potassium phosphate, a 6 before potassium nitrate, and then no coefficient in front of lead 2 phosphate. And now on both sides, I will have 3 leads, 6 nitrates, 6 potassiums, and 2 phosphates in order to balance my equation.